Good evening, everyone. This is your host Amina for tonight. I would like to welcome you all to the Society of Petroleum Engineers, University of Bahrain Students Chapter. Thank you all for joining to our very first event of this year, and I'm sure you guys will really enjoy it. I would like to make an announcement that we will be having a group photo at the end of the session, so please be ready for it. Now, I would like to introduce to you to our speaker, Mr. Yasser Thara. Mr. Yasser is a reservoir engineer at the Wintersheel Dea in Germany. He holds a master's degree in petroleum engineering from Imperial College in London. He has also contributed to the Northern Lights carbon capture and storage project with the support of Shell. Now, I would like you to please welcome Mr. Yasser. And if at all anyone has at the end of the presentation any questions, please send them in the chat. Mr. Yasser, please go ahead.
Thank you, Amina, for the introduction, for your kind words, and welcome everyone. To be honest, I'm not sure if I should say good evening with what's happening around the world, but I was actually thinking if we should actually do this right now. But I think the world goes on, and we have to kind of live with it. Thank you, SP Bahrain, University of Bahrain chapter, for inviting me as a speaker. Actually, so today I'll just talk. I'll spend a few minutes about the role of carbon capture and storage in energy transition. And as Amina mentioned, I've worked on this topic during my master's and then also after my master's, and right now at Wintersheel Dea as well. I'm about to join the carbon management group in the company. So I'm really looking forward to it, and I'll just try to share my knowledge with you guys today, and then hopefully we can have some fruitful discussions in the end. For those who don't know me, I'll just give a small background of where do I come from. So I was born and raised in Pakistan. You can see me here as a kid back in Pakistan. And then back in 2014, I moved to Turkey and Northern Cyprus to do my bachelor's in petroleum and natural gas engineering at Middle East Technical University in Northern Cyprus. And during this time, I also went to Poland to participate in the SPE's East Meets West Congress. It's an annual conference in Europe. And there I was the winner of the SPE Student Paper Contest that year in 2018. So here's me with Darcy Spady, the SPE president at the time. And after finishing my bachelor's in Turkey and Cyprus, I then moved to UK to pursue my master's in petroleum engineering at Imperial College London. And actually, this is where I was introduced to the topic of CCS, where I saw the world-class research being done on the topic and how people are really aware of what happens with the climate, which is why I decided to do my master thesis with Shell Norway on the Northern Lights CCS project, which is a really great project. It's one of the biggest European carbon capture and storage project, which will be coming live in the coming years. And after finishing my master's at Imperial College, I now work at Wintersheel Dea as a reservoir engineer in Germany. I'm right now sitting in Hamburg, and we don't know what happens in future, but hopefully I stay here for some years to come. So with that being said, let's quickly look at what we'll talk about today. So I want to talk with you guys about four things. The first one is why is everyone talking about energy transition? I mean, what's the hype about it, So I'll try to demonstrate or create some premise onto why we need to have this discussion right now. And then we'll also talk about what is CCS, because this is also something that has been spoken a lot about on social media or in general in print media, but a lot of people don't actually know what is CCS. And then I try to combine these both into explaining what is the role of CCS in energy transition and why all the companies in the world are now trying to shift their focus towards CCS. And lastly, I'll spend a few minutes to discuss what are the challenges that await for us when we try to deploy CCS on a large scale. So that being said, for any one of you who follow LinkedIn or news in general regularly, you must have seen these buzzwords out there like sustainability, net zero, energy transition, carbon neutral. Any company right now in the world which emits a lot of carbon dioxide or greenhouse gases, they want to include these hashtags into their LinkedIn posts or social media posts or even their websites. I mean, you can open any website right now, and I can guarantee you will find these words in their company strategy section. And what I want to do right now is to kind of break it down. I mean, why is every company now all of a sudden so aware of energy transition, or why do they want to become carbon neutral, right? So to understand that, we need to understand a bit of history. We need to understand how we modernized over the last 3 centuries. Here I have a picture of England from 1700s. Sorry, it's obviously a painting, and you can see how old age this painting looks. I mean, you can see brick houses. You can see no electricity, no transportation, right? And compared to that, this is how London or England in general looks like right now. I mean, with all the modern transportation systems, with high-rise buildings. I mean, we are technologically, we have come really far ahead. I mean, from 1700s to 2000 or to right now, we have created steam-powered engines, electricity, coal-powered fuel stations, cars. We discovered oil. Wright brothers invented the plane. We had the internet bubble. Right now, we have phones and laptops at our ease. And obviously, we have high-rise buildings. So, I mean, we came a long way in these last 400 years. And I mean, yes, this is a great achievement for humanity, right? But it comes at a cost. And that cost has been the global climate. So if we look at the global temperature over the last 400 years on the same scale, we can see how the global temperature has skyrocketed in the last 100 or the last century. So the y-axis here is actually showing the increase or decrease in temperature. And up until 1900s, we were kind of stable in the global temperature. But since the end of 1900s or since the industrialization era, the global temperature has been just going up and up and up without any remorse. And this is actually really dangerous for the climate and for humanity or for any living things living on the earth. I mean, just imagine your house warming up 1.5 degrees every year, which is not good for us. So I'm not going to talk a lot about how the global warming is happening, because I guess we all kind of understand the greenhouse gas emissions, and then they kind of trap the heat into the atmosphere, rising the temperature. But what do I want to talk about is which sectors or what human activities cause the most greenhouse gas emissions. And I guess it's really natural for us to understand that it's the energy sector, because the energy sector does not really mean oil and gas or fossil fuels. The energy sector means all the energy that we humans consume for a daily life. So it includes energy in the buildings, in the transport, in industries. I mean, industries could be any industries like steel manufacturing, cement manufacturing, road, transportation. So we require a huge amount of energy to kind of support the global population that we have right now. And as you can see, around 73% greenhouse gas emissions right now come from the energy sector. But we should also kind of understand how are we creating our energy, because there are different ways of creating energy right now. We have biomass, we have renewables, we have fossil fuels, and a lot of other things. And if you kind of break it down to what do we consume as humans to create energy, then we see the real picture that we actually consume coal, oil, and natural gas to a really high extent in the current days. So a lot of energy that we produce actually comes from burning the fossil fuels. And again, I think it's kind of general knowledge now that when we burn the fossil fuels, we create carbon dioxide, which then goes into the atmosphere, contributing to the greenhouse gas emissions. So here I have a picture or a graph of the annual CO2 emissions that come from burning of fossil fuels. And again, it's kind of intuitive that or kind of synchronizes with the industrialization era, that since we created all these fuel-powered stations or engines or cars, the CO2 emissions have been rising and rising. And I mean, they have been rising at an alarming rate. And right now we stand at around 35 billion tons of CO2 emitted into the environment every year. I mean, there was a dip because of COVID, but it is expected in 2021 and 22 to this for this amount to go back up again to around 36 billion tons. However, that's not the complete picture. That's one side of the picture. The other side of the picture is what's coming ahead of us. I mean, what's next? What's the future? And it is estimated that by 2050, the global population will have risen up to 10 billion people. So right now we're somewhere below 8 billion, and imagine 10 billion people living on the earth. So according to the US energy agencies, the global energy demand will grow by 47% by 2050. And if we are increasing our population at such a rapid rate, then we need to provide energy. And right now, the cheapest or the most efficient way of making energy that we humans know is the fossil fuels because of the high energy content that they have. Which is why a lot of energy agencies still believe that oil or fossil fuels will still play a huge role in the energy mix in future. So just to comprehend more on the role of fossil fuels and how they will play a role in the future, here I have three different graphics, and they all come from the International Energy Agency. And this is one of the biggest agencies that is kind of trying to model the future outlooks or the future world energy scenarios. And they've done quite a lot of work into understanding how can we reach net zero emissions by 2050. So here we look at three different scenarios. This first scenario is called the stated policy scenarios or STEPS scenarios. And this is the scenario where they model what will happen by 2050 if we go forward with the stated policies. So whatever that already exists in all the countries. And the orange line here shows the global carbon emissions. So as we can see, these emissions are coming down, but they're nowhere close to zero. And our aim is to actually reach net zero by 2050. So this is not happening in this current scenario. And one of the biggest reasons why it's not happening is because a lot of energy still is coming from the fossil fuels. So in the current scenario, a lot of countries are still using fossil fuels to produce energy. And if we go forward with the same approach, we are not reaching net zero anytime soon. The second scenario is called APS, which is announced pledged scenarios, which talks about the promises that countries have already made. So a lot of countries have, come up and said like, yeah, we want to become net zero by 2030, by 2050, by 2060, different timescales. And they've announced new policies, they've announced new environmental regulations or new laws or carbon taxes. But even then, even if we include all these pledges into our scenarios, we are not reaching net zero. And again, you can see the fossil fuels are playing a huge role. So people at IEA or the International Energy Agency then decided to see, okay, what do we need to do to reach net zero emissions? And that's the third scenario, the NZE, net zero emissions. And they kind of modeled what would be the energy mix if we were to achieve net zero. And quite intuitively, the renewables now occupy more than 50% of the energy mix. I mean, that makes sense because we want low carbon energy sources, right? But still, that being said, we would still need oil, gas, and coal in our energy mix because not every country in the world has the infrastructure or not every industry in the world can survive purely on renewables or other energy systems. So the idea here is that we need fossil fuels and we will need them in future. And it is possible to reach net zero with fossil fuels. So before we move forward, I just want to give us a brief timeline of the climate change targets because I'm not sure if you guys have heard of these 1.5 degrees C or 2 degrees C or the Paris Agreement, because these are, again, some terms that you keep reading on internet, but a lot of people don't actually understand what this means. So back in 1988, we established something called IPCC. It's the Intergovernmental Panel on Climate Change. And in 1992, the first framework or the convention was signed on climate change. So this was actually the first time we realized, okay, we are doing something wrong. The global climate is just going haywire, so we need to do something about it. And the outcome of this convention was the Kyoto Protocol. So 192 countries or parties signed this protocol, and this was the first time countries made a commitment to reduce greenhouse gas emissions. But even with these three activities in 1990s, we didn't really do much. I mean, the climate didn't become any better. We didn't reduce the greenhouse gas emissions to an extent, and things just stayed as usual. Until 2015, I mean, this is when social media and people kind of like kicked off and people became really aware, like there was this huge wave. You must have heard about Greta Thunberg or a lot of other climate activists which came on, and this is actually when we humans or governments actually started taking climate change seriously. So you must have heard of Paris Agreement. So this is when all the countries of the world met in Paris and for the first time, we made a legally binding international treaty on climate change, and a lot of countries, I think most all the countries signed it, where it was pledged that we want to keep the global temperature below 1.5 degrees Celsius. And in the scientific community, it is believed that if we keep the global temperature at 1.5 degrees Celsius, we are still not good. But if we reach the 2 degrees Celsius mark, then that's the point of no return. So that is considered as damage beyond control. And this is why right now, or what the Paris Agreement says, is that we want to keep the global temperature below 1.5 degrees Celsius. And if you remember from a few slides ago, we already are at 1.3 or 1.4 degrees Celsius, which means that it's not far ahead in the future that we'll breach the 1.5 mark, and it is actually expected to reach 2 degrees Celsius by 2030 if we continue with the current activities that we have. And then the latest meeting that the countries had was COP26 last year in November in Scotland, which is where they kind of completed the work they started at Paris Agreement, and almost all the countries of the world have now rolled out a new climate change initiatives or their national plans on how they want to reduce the global emissions, at least in their countries. With that, I hope I could create some premise for why energy transition is such a buzzword, or why we need climate change discussions right now. So I would like to move on to the second buzzword for this talk, which is CCS. I mean, a lot of companies now are talking about CCS, but let's break it down. I mean, what is CCS? So I decided to use this really simple schematic. CCS in reality is not as simple as it looks like on this picture, but I just want to use this to explain what is carbon capture and storage. So CCS stands for carbon capture and storage, and what we essentially are trying to do here is we want to capture the carbon dioxide at the source. So imagine this is some sort of industry. It could be cement, steel, any industry which emits carbon dioxide. And we want, instead of letting CO2 go out into the air, we want to capture it at the source. And then we want to, I mean, it could be with pipelines, it could be with ships or tanks, but the idea is to capture it at the source, transport it back to a subsurface system where we can store it under the ground permanently. So that is the capture aspect of CCS, and that is the storage aspect of CCS. And don't get me wrong, there are a lot of variety of methods out there to capture CO2. There is direct air capture, there is biocapture, there is capturing at the source. But that is not my area of research or my area of expertise. So if you are really interested in capturing aspect of CO2, then you can read a lot of different articles. I also have a reading list in the end that I'll share with you. So yeah, feel free kind of research into this topic, because this is really interesting on how can we capture high amounts of CO2. But what I do have some knowledge on is the storage aspect of CCS. So when you talk about storing CCS under the ground, I mean, it's not as simple as drilling a well and putting CO2 into the ground. Obviously, there are certain requirements that we need to meet. So first of all, we need to identify that there are two kinds of reservoirs or two kinds of subsurface systems where it is ideal to store CO2. One of them is deep saline aquifer. So it's the salty waters that are really deep, because we don't want to contaminate the fresh water sources that we use for daily life purposes. So we want to target the deep reservoirs which have saline water, or we can also target the depleted hydrocarbon fields, because depleted hydrocarbon fields are something that we produce from, right? So we understand what happens there. We understand the physics. We understand the chemistry of this entire architecture of the reservoir. And because they're depleted now, which means there's a lot of space for us to put something back in. So it is kind of like reverse engineering about something that we have been doing for the last 100 years. You know, we have been producing oil and gas, but now we want to kind of reverse engineer it to put something back into the ground. And then there are some requirements for CCS. So first of all, we want the reservoirs to be deep enough to maintain high pressure and high temperature. Because when we capture CO2 and when you transport it, you don't do it in gas form. We capture and transport it in liquid or supercritical form. So high pressures, high temperatures, or it depends on the geochemistry of the fluid. But when we inject it back into the ground, we want to keep it in the same state, because if CO2 starts forming back to gas, it will create a lot of flow assurance problems as well as storativity problems into the reservoir. The second condition is that we should have enough connected pore volume, because we are not talking about once in a lifetime injection of CO2. We want to keep injecting CO2 for long years to come. I mean, the Green Science project, for example, that Wintershall Dea is a partner at, the plan is to inject 1 million tons of CO2 per year. So that's a really high amount. And to accommodate this huge amount, we need space. And in terms of reservoir engineering or in terms of subsurface, it's called pore volume. Then we also want some sort of sealing impermeable cap rock. So imagine this as some sort of a seal, because when we inject CO2 into the ground, it's less dense than water in the ground, and it will kind of rise up due to buoyancy. So we want something on the top that kind of stops it from rising up to the fresh water or the water table, or in worst case, rising up back to the atmosphere. So we want some sort of a seal impermeable cap rock. And the last thing that we want is structural trap to contain the CO2. Because if CO2 cannot go up, then it will for sure move left or right, because we are injecting with high pressures. And then, basic diffusivity, high pressures at the well will mean that the CO2 moves laterally. So we want it to trap somewhere. I mean, and this is where the structural trapping comes into play. So imagine here we have a fault in the subsurface and a cap rock on the top. So once CO2 reaches here, it cannot escape from here. Or in this case, some sort of pinch out. So there are a lot of different kind of trapping mechanisms in oil and gas industry that we learn about. But the idea here is that we are looking for some sort of structural trap. So while on the topic of trapping, it's not just the structural traps that I talked about earlier, but there are also other microscopic trapping mechanisms that are coming into play. And that is what we as reservoir engineers are trying to kind of capture or maximize, so we can maximize the storage capacity of a reservoir. So I already talked about structural trapping, but the other kind of trapping that we're trying to achieve in the reservoir is residual trapping. And I don't want to be really scientific about it, but this is basically when we inject CO2 into small pores. So imagine like very small holes. If the CO2 pressure is not high enough to kind of enter into a pore or enter into a pore throat, then CO2 will not be able to move in. And this is kind of like the capillary pressures that we're trying to achieve, where the CO2 gets trapped and does not have enough pressure to move into the next pore, let's say, which is what we're trying to achieve with residual trapping. The other kind of trapping, which is very important for us, or our best chance at trapping CO2, is solubility trapping. And this is, again, something to do with chemistry. So when we inject supercritical CO2 into saline waters, CO2 tends to dissolve in this water. And once it dissolves into the water, it creates this mixture, which is actually heavier than pure CO2 or pure water. So it has a higher density than both these states. And then it would kind of start sinking towards the bottom of the rock, bottom of the reservoir. And this is actually the best kind of trapping that we're trying to achieve, because then we can be really sure that CO2 is not moving upwards, it's not moving laterally, it kind of sinks back into the ground and just stays there. And this would be kind of like the ultimate goal that we want to achieve with CCS. And the last kind of trapping that we kind of look into is called mineral trapping, again related to geochemistry. And this has to do with CO2 reacting with salts in the water. So imagine a saline aquifer with high concentrations of NaCl or calcium or magnesium. And then when CO2 comes into play, it reacts with these salts, creates these solid precipitates of sodium carbonate or calcium carbonate. And then again, imagine really small holes, and then you introduce solid precipitates into it. So it kind of creates the hole even smaller. And then residual trapping comes into play, where CO2 cannot move anymore, so it kind of gets trapped in there. So there are a lot of different kind of trapping mechanisms that we're trying to achieve. And this is the kind of things that we in the oil and gas industry are now trying to understand more about, so we can know where our CO2 will end up when we inject it into the ground. So with that being said, I remember last year I was giving a presentation on CCS at a seminar, and there was this one question that was asked to me, and I was really surprised actually that people still believe that CCS is something far in future, or it's a myth, or it's a technology that we cannot really deploy on a large scale. And it's surprising for me because this is not something new. This is not something out of the world. This is something we have been doing for over 60 years now. Back in 1972, the Terrell natural gas processing plant in Texas for the first time captured CO2 on the plant itself, and we injected back into the ground for EOR purposes. And for people who are not from oil and gas backgrounds, EOR is enhanced oil recovery. So we inject CO2 into the ground to produce more oil. And this is something that has been studied, well published, well researched, and has been going on for the last 60 years in a variety of projects around the world. So as I said, CCS is not something new. We know this. We have been doing this for a long time. And as I mentioned back in 1992, when the first time we actually talked about climate change, Norway introduced a carbon tax. So in 1996, the first CCS project was initiated, which was in Sleipner license in Norway. So here I have a small map. So this is Scotland, this is Norway, and that's the North Sea. And the operators of Sleipner license, Statoil at the time, which is now Equinor, they kind of understood that it's actually more expensive for them to emit CO2 back into the environment rather than storing it under the ground. And that's what they did. And they have been doing it for almost 30 years now. So to give you some context, these are the seismic images that they capture every 3-4 years in Sleipner formation, in Utsira formation, in Sleipner license. So in 1994, you can see the cap rock here in the dark because of the high density, with no fluids there. But then in 1996, when they start injecting, you can see the difference in the reflections of seismic waves. That kind of shows the carbon dioxide in the subsurface, and then over the years you can see how it's kind of growing. The plume is moving laterally left and right, but it's not moving upward. So the cap rock is doing its job to kind of keep it under the ground. So I hope now you have some idea of what's CCS and what's energy transition, and now I guess it's time to bring them together. So what is the role of CCS in energy transition? That's the entire point of this webinar or this presentation itself. And to explain the role of CCS in energy transition, I'm going to use this image. I'll explain you. It's from the Emissions Gap Report by the United Nations Environment Program, and it's something that explains really nicely why we need negative CO2 emissions or negative emissions technology like CCS. These are called carbon removal technologies. So on the y-axis, we have the greenhouse gas emissions every year. We have already talked about CO2 emissions around 33, 34 gigatons per year. Greenhouse gas emissions in total around 48 gigatons per year as of now. And the yellow line here shows the emissions in business as usual case. So what that means is if we continue doing what we do without caring for the climate, the emissions will keep rising until we reach a point where the environment or the global climate is so bad, it's so harsh, that we'll have so many natural disasters, we'll run out of resources, we'll most probably have more wars, and it will be a point where the global population will actually not be able to survive on the planet. So the population will actually go down. And this is why you see the global emissions coming down. So this is for sure not a good idea, right? We don't want to be there. We don't want to reach the stage where the climate kind of resets itself, which would mean a lot of loss of life. So then we talk about conventional abatement technologies. And these are all the technologies where we are like, okay, we don't want to produce more CO2. So we switch to renewable energies, we switch to more fuel efficient technologies, we stop using coal, we stop using oil and gas as much as possible. And even with all of that, let's say we do everything that we can do to remove CO2, we would not reach net zero emissions even by 2100. Even though right now we want to reach net zero emissions by 2050, but let's say by 2100, we are not getting there. So what do we do then? This is where carbon removal technologies come into play. And it is actually expected to start removing carbon from the environment by 2030. And if we start removing carbon at this rate, this is the only way we can actually stay below 2 degrees Celsius by 2090. So not even 2050, by 2090. And then you can see how bad the situation is right now and why we need to scale up CCS at a really large scale and kind of rapidly do it to remove more and more carbon dioxide to kind of achieve this below 2 degrees Celsius mark by 2050. So again, this has been identified by a lot of countries, by a lot of organizations around the world, and I'm actually really happy that now this is something that a lot of companies talk about, and a lot of work is being done on this topic. So, according to the Global Status Report by the Global Carbon Capture and Storage Initiative, by September 2021, we have over 100 CCS projects in the pipeline, out of which around 50 of them are already in advanced development and the rest are in early development phase. And here you can see on the map, they're spread all across the world, especially in Europe and in US, which are kind of like spearheading this movement of CCS to remove the carbon emissions from the environment. And if you look at what's happening on the global scale in terms of countries announcing CCS in the national long-term strategy, around 83% countries in the world now recognize CCS as a technology that will be really helpful in their long-term strategy to achieve net zero targets. But the main takeaway from this slide is that to limit global warming to 2 degrees Celsius, we need to scale up CCS to 5,600 megatons per annum from around 40 megatons per annum today. And you can now kind of understand how big the challenge lies in front of us. I mean, right now we have a capacity of around about 50 megatons per annum, and we need to reach 5,600 megatons per annum. And this should create some questions in our head. I mean, we are talking about huge amounts of carbon dioxide being stored into the ground, but do we really have capacity to store it? And the answer is yes. So according to the International Energy Agency's scenarios, we need to store 140 gigatons of CO2 by 2060 in total. And if you look at the global map, I mean, these are some preliminary studies. These are not the final results, but even right now, we have a lot of motivation, or we have a lot of support actually, that we do have more than 160 gigatons of storage capacity. US alone has 2,300 gigatons of storage capacity. Then you have Europe, you have China, Canada, and so on. So with that being said, again, this should raise some questions as to the value chain for CCS. How do we create money out of it? Because this is something that will not generate you money. However, thanks to these climate initiatives that we have now, a lot of countries, a lot of regions have started imposing carbon taxes. They have started imposing strict regulations that we're not allowed to emit carbon into the environment, which then makes CCS kind of profitable. I already gave you the example of Sleipner, but I'll give you another example of the European Union, for example. So in EU, we have something called EU ETS, which is the emissions trading system. And every installation or every industry gets a certain allowance of carbon emissions that they can emit. And if they want to go beyond that, then they have to buy these emissions. And here you can see the price of per ton of carbon dioxide emissions. I'm sorry for the unit here, but it's in euros. So you can again see since 2017, or actually since Paris Agreement, the price of CO2 tax has risen to some extent. It's right now it's 70 euros per ton, and it's actually expected to be above 100 euros per ton very soon. So that's one reason why companies now, instead of paying this much money for the CO2 they emit, they are looking into storing it back into the ground, which would actually be more economical for them rather than paying the carbon tax. Then a lot of countries have introduced government funding for CCS projects. So if you start doing a CCS project as a company, you get funded by the government, which is obviously good for you. You can get subsidies in form of tax credit. So this is the model that's being used in the US, for example. It's called 45Q, if you want to read more about it. But what it basically means is if you invest some money in CCS right now, then you can get back it in form of tax return over the next 45 years, which is again something good for the companies given the inflation and the interest rates. And obviously there's a huge positive motivation for funding into this technology, because right now it's a really expensive technology. But imagine oil and gas 200 years ago. It was really expensive and no one wanted to be in this industry. But right now, oil is actually cheaper than water. And that's because we did so much research, we created so many technologies that it became really easy for us to produce oil and gas. So similarly, if we do the same kind of scale up into CCS, then who knows? I mean, 50 years from now, CCS could also be a cheap technology or a cheap fix to the carbon emissions into the environment. So because we are majority of the audience here is from Bahrain or from Middle East, I decided to put together 2 slides about the scope of CCS in Middle East, or especially in Bahrain. So the first graphic I have here is the distribution of annual CO2 emissions worldwide by countries. And if you look closely, the first country or the country with the highest CO2 emissions is China. And it's no surprise, it's the country with the biggest population, with a lot of industrialization happening in the recent years, and followed by United States and then EU. So these are 3 of the world's most developed regions, and they have a lot of high CO2 emissions, which makes sense. And then you have India, Japan, Russia. But what's interesting here is there is no Middle Eastern country on this pie chart. So all the Middle Eastern countries go up into the 28% rest of the world, even though Middle East produces the most amount of hydrocarbons in the world. And why is that? It's because this is showing the global emissions by the countries. But then I would like you to look at the next picture, which is the per capita CO2 emissions. And that means we are now looking at the emissions divided on number of people that live in the country. And that actually shows that the Middle East actually emits more CO2 than China. It's even more darker, because the population of the Middle Eastern countries is not as high as China, but and then they do emit a lot of CO2, which means that on per capita basis, things in Middle East are actually really bad, and something needs to be done about it, right? So again, I just put this one slide about Bahrain because I actually found it really interesting. So in COP26, which I talked about in a few slides ago, last year in November, the official statement by Bahrain at COP26 was that they want to achieve net zero by 2060 using circular carbon economy, which basically means they want to use carbon removal technology. So even in their official statement, they mentioned carbon capture technologies, which they believe is essential. And Bahrain is one of the 3 countries in the Gulf Council which have included CCS as a mitigation measure in their intended nationally determined contributions. So it's in the long-term national plan. However, right now, there are no CO2 or CCUS specific regulations in any GCC country, which is why it's a region where we have a high CO2 emissions per capita. And when we talk about CCS in Bahrain, the mechanism that they want to use is called the utility subsidy reduction mechanism, which basically means that if you, as an installation or as an industry, want to deploy CCS, then you can get some sort of subsidy in the price you pay for your electricity or for your water or for your gas or something like that. So they want to provide subsidies in utility in return for initiating CCS. With that, we come to the last part of this presentation. What are the challenges for CCS? I mean, why is CCS still at 40 megatons per annum and not 5,600 megatons per annum? And one of the biggest challenges we have right now is the capture technology. This is something that we still are trying to figure out. How can we capture high amounts of CO2 from the air directly? But it's really expensive. And again, it requires a lot of chemistry and chemical engineering knowledge, which I don't have. So I'm not going to talk about it a lot. But what I do know is that there are also other challenges. So for example, when we talk about subsurface, we need to make sure about the caprock integrity. We need to make sure of the plume monitoring. So that's actually my thesis topic from a master's. How do we monitor where the plume is traveling or where CO2 is traveling, and if it is leaking out or not from some sort of pathway? We need to talk about injectivities, because when we inject high amounts of CO2 with high pressures into the ground, this could create some sort of fracturing in the reservoir, which can also then lead to induced seismicity, which is why right now CO2 storage onshore is not allowed, at least in EU. Because, for example, here in Germany, people don't want us to be injecting something under the ground, which can then create an earthquake up on the surface. So these are the challenges that we in the reservoir engineering community are trying to figure out or trying to research more into to get more answers about Then we also have economic challenges. So one of them is actually the capture technology because it's really expensive, which then drives up the cost of CCS. So right now it is estimated that the cost of storing 1 ton of CO2 is around $125. And I showed you already in European Union, the carbon tax for 1 ton of CO2 is around 70 to 80 euros. So you can already see that the cost of emitting CO2 is 70 or 80 euros and cost of storing CO2 is 120 euros. And the day they both come together, or the day the cost of storing CO2 goes down, then it would be the most economic scenario rather than emitting CO2. And the other challenge is creating industrial hubs. Because, for example, we at Wintershall Dea, we have the know-how and we have the subsurface aspect of storing CO2, but we also need CO2 to store, right? So we need someone to give us the CO2 that we can store into the ground. So we need to then create some sort of industrial hubs. So industries that emit high amounts of CO2 are then connected to industries that can store CO2 into the ground. And this is the kind of cluster that we're trying to create, at least in Europe. So for example, Northern Lights is a really great example. Greensands, Humber project in UK. These are some examples of the industrial clusters that they're trying to create. And then we have geopolitical challenges. For example, cross-border transportation. So right now, according to London Protocol, it's not allowed to actually transport CO2. Let's say, for example, Greece. It's a country in EU with not a huge amount of hydrocarbon reserves, or it's not a country known for oil and gas. And then you have France, which has Total operating there, a huge know-how of CCS, or Norway, for example, but it's not allowed to kind of transport the CO2 cross-border. I mean, it's complicated. And then you also have this question of who takes the responsibility. I mean, right now, the underdeveloped world is being pressured to not use fossil fuels, but all the developed countries, for example, US, UK, EU, China, they all used fossil fuels historically to be where they are right now. So then the question is, who takes the responsibility? I mean, should the countries that emit the most CO2 or be the champions of CO2 storage, or should it be divided equally among the countries? So these are the kind of discussions happening on a global scale right now as to how can we reduce carbon from the environment. But there are also things that we as humans on an individual basis can do to reduce the carbon footprint. So an average, according to Nature Journal, an average carbon footprint in US emits 16 tons of CO2 per year. And globally, the average carbon footprint is 4 tons. And to have the best chance of avoiding 2 degrees C rise, this average global carbon footprint needs to drop to under 2 tons by 2050. So we need to halve the amount of our carbon footprint. And I just wrote down some cliched mainstream things that we can do, but sometimes we don't realize that we are doing it, or we are not doing it. For example, turning off the appliances when not in use, or switching to more energy efficient appliances. Using multi-use cups rather than paper cups. I mean, it's really common to go to Starbucks, grab a cup of coffee in a paper cup, but you have to think about, what am I doing? You can obviously cycle to work rather than driving a car, or use public transport if possible. And you can obviously avoid using plastic bags, reduce the use of paper, and use recyclable materials as much as possible. But in general, the main takeaway here is that be aware of your carbon footprint and try to minimize it as much as possible. Because whenever I see people blaming fossil fuels or oil and gas industry, and I work in the oil and gas industry, I kind of feel this hypocrisy when people don't really reflect on their own actions and they blame someone who's actually providing energy for the world. So, as I said, these are some useful readings that I used for this presentation, and these are in general really good readings for you to have knowledge on CCS or climate change in general. So I'll share them with you in the chat after the presentation. So feel free to give it a read, and I'm sure you'll enjoy it. Obviously, I would like to thank some people, Professor Sam Crever and Martin Blunt from Imperial College London. These are the two people who have really taught me a lot about CCS. Sam was my thesis supervisor actually at Imperial, and they are doing some world-class research at Imperial College on CCS from pore scale to global scale. Ragad and Nihal from SPE, they also have like really helped me in compiling this presentation and also in general to do more activities with SPE. And Guillaume from Shell, he was my second supervisor for my master thesis. And again, a lot of my knowledge about CCS is thanks to this guy. So with that, I guess that's it from my side. Thank you so much. And I would love to answer any questions that you may have.
Thank you so much, Mr. Yasser. It was indeed very informative and very useful. Honestly, I really enjoyed it. It was very interesting. If at all anyone has any questions, please raise your hand so that we can go in order and you can open up your mic and you can ask your question itself. Otherwise, if you cannot open the mic, you can write the question in the chat. We have yes, Sarwa, go ahead.
Yeah, I was just wondering, first, thank you so much for the amazing presentation. I learned a lot and I absolutely am amazed by the technology that we're working on now because it will really make a huge change. I was just wondering, okay, you said that mixing CO2 with saline makes a mixture that is more dense than water. Why don't we just store it in a container that already has saline solution or that is connected to a pump that automatically pumps in saline solution when CO2 comes in contact with the material, with the internal material of the container? Therefore, we would decrease the density before we even pump it into the ground, making the trapping challenges limited.
Honestly, I mean, I've already said this. I'm not an expert on CO2 capture technology, so I'm not sure if this is a good idea or not. But I would say that CO2 storage, or in general CCS, requires a huge amount of energy itself. When you want to capture CO2 or when you want to pump it back into the ground. And the entire idea here is to reduce the emissions that we create. So if you involve another pumping mechanism or another use of water into it, because water is also a scarce resource. I mean, we don't have a lot of it. So what you're talking about right now is first we have to get the saline water up to the ground somehow, which would require energy, then mix it and then pump it back, which would require more energy. So again, I'm not sure about this, to be honest, because I don't work in capturing, and maybe someone in the chat here who's a chemical engineer might know more about it. But in general, I believe that when we are injecting CO2 into saline aquifers, because this is something that naturally exists under the ground, so we don't really have to make any more human effort into it. And when we capture CO2, it's already captured at high pressures, so it's already in the supercritical liquid form. Then it naturally makes sense for us to then just put it into the ground and hope for it to react with the saline water under the ground, rather than adding more energy or more complication on the surface. But that being said, I'm sure there must be a better answer to this question by someone who's more expert on this matter. So I'm really sorry.
Thank you so much.
No worries. I can see a question.
Would you like to speak? Yes. Iman is asking how successful is the integration between EOR and CCUS?
So I don't have numbers like in terms of figures right now with me, but CCUS, which is carbon capture and utilization and storage. So when we put CO2 into the ground for EOR purposes, that is something that has been done around the world in a lot of projects. And I personally worked on an EOR project last year. So it can increase your production by 10%, in really good cases, maybe 15%. And that's, I mean, if you look at it in a way that you do want to remove the carbon dioxide from the atmosphere, so when you put it into the ground, you're already earning money out of it, and then you produce oil, which is then more money. So in general, it makes it a really economic case to do CO2 EOR. But that being said, CO2 EOR is not applicable in every reservoir in the world. because there are certain requirements that have to be met. For example, minimum miscibility pressure, capillary pressures, or the depth of the reservoir, pressures, temperatures, all these things. So it's not as simple as doing CO2 EOR in every oil reservoir in the world, but where it's actually possible, it is being done. And it can generate additional oil for maybe 10% more recovery or 15% more recovery in really good cases. I can see another question in the chat. It's what are the things
All right,
we
thank
should...
you, Mr. Yasser. We have Dr. Muhammad bin Shams over here.
Okay.
Assalamu alaikum. Thank you, Yasser. Very interesting presentation. I learned a lot, and I believe that everyone here learned a lot about this interesting topic.
Oh, the doctor is raising her hand, so yeah.
Yeah, I'm talking. Can you hear me?
Yeah, I can hear you. I guess there's some lag with Amina, but go ahead, ask your question.
Okay, Yasser, can you please show me the slide 20?
Okay, let's go here. Yeah.
Okay, well, this is a very interesting slide for me. Now, I just trying to appreciate how important the topic is for us here in the Middle East, more focusedly on GCC or Bahrain. Now, my question is, which is more important, the picture on the left or the picture on the right? Because I believe the one which is more harmful is the one on the left, but the one on the right show me that like the people who are not really polluting are kind of more responsible of what's going on. But the one on the left tell me that the giant industrial country are emitting a lot, so they are the one who should be responsible of the emission. So I don't know, it's like a confusing me. So can you elaborate more here?
Honestly, there is no right or wrong answer here. I mean, this is one of the things what I meant by the geopolitical challenges. Who takes responsibility, right? Because you can go up and say that we should blame the industrialized nations because they are the ones which emit the most amount of CO2. But at the end of the day, the question is, where do people live and how much CO2 comes out from that place? For example, in Africa, you don't see a high amount of CO2 emissions because they are not so developed. This does not mean they don't have a lot of population. It's just they are not that developed. However, in terms of Gulf countries, they are developed, but they don't have high population. So this is kind of trying to find the right balance between, do you want to blame a country or do you want to put the blame on the people living in those countries? And honestly, I personally, if you ask for my opinion, I believe this has to have some sort of reflection of historical emissions. I mean, countries like US and EU and China have been industrializing for last 3 centuries, and they have used fossil fuels. So it is right to blame them for the global climate change that has been happening for last centuries. But that does not mean that all of us don't have any sort of responsibilities on us. So it's kind of like a top-down change. So obviously it has to come from the governments which are emitting high amount of CO2, but then it also kind of trickles down to individuals at the end of the day. So on all of us to kind of be aware of our carbon emissions and what we do, what are our activities, which would then also bring down the per capita CO2 emissions in each country. So I guess it goes hand in hand. There is no right or wrong answer. There is no right picture here. But this is an interesting way of showing that sometimes the countries that emit the most CO2 are not necessarily the ones that are emitting the most CO2 per capita. For example, China emits the most CO2, but that's because they are the biggest population in the world. So I guess, as I said, there is no right or wrong answer, but the change has to start somewhere. And I guess it shows really nicely, for example, in this picture here, that EU and US and also China, I mean, these are the 3 biggest nations that are front runners in CCS industry right now. So I think they do take some sort of accountability. and they are already working on it. The other thing, I'm sorry for the long answer, but the other thing I actually did not include in my presentation was the emissions. So there are three different kind of emissions. There is scope 1, scope 2, and scope 3 emissions. I don't know if you know about these, but scope 1 is the direct emissions that come out of directly from you. For example, if you are an oil and gas platform, so the direct emissions that you produce. Then you have scope 2 emissions, which are the emissions that are being generated because of your activities. So when you buy electricity or when you order some material and it comes to you, it's transported to you. So there are some emissions, and those are scope 2. And then you have scope 3 emissions, which are basically when your product is burned in the world. So, for example, Qatar produces a lot of gas, then it sells it to other countries, and then it is burned in those countries. But essentially, those emissions could be traced back to Qatar, right? This is why actually Middle Eastern countries or the GCC has a really high emissions if you take into account scope 3 emissions, because they produce a high amount of carbon dioxide, hydrocarbons. So at the end of the day, when we talk about net zero, our aim is to actually reduce all three emissions, scope 1, 2, and 3. And if you think in this line, then then Middle East has a huge responsibility to kind of reduce their scope 3 emissions because of the hydrocarbons they produce.
Thank you very much.
No worries.
Yes, Arwa, you can go ahead and ask your question.
I was just wondering, okay, so we have, where can I research more about this? But I don't only want to research, how can I already have, like, I'm a chemical engineering student now. So
Okay.
I'm still not like, I'm a major, not yet a chemical engineer. So how can I be active in this, basically? I don't just want to research about it, especially that it's a very interesting thing for me.
Honestly, I would say the best way would be to first of all do your research and understand which organizations are working for it, and then I would say kind of try to get involved with these organizations if possible for you. So, for example, now SPE itself has its own climate change committee. That would be one thing. You could always get in touch with International Energy Agency or UNEP. So it depends on you. For example, I'll give you an example of this one company. It's called Climeworks in Switzerland, and that's, I would say, the champion in capturing technology. As a chemical engineer, I guess that would be the most interesting for you. And you could always try to look for jobs when you graduate in this industry, or you could go into the research or academia aspect of it. I can give you my own example. I'm a reservoir engineer by background, but I studied petroleum engineering all my life. But now that I work at Wintershall Dea, from the very first day, I knew that this company has a really good CCS program, which is why I wanted to work for them. And I tried my best to be part of the CCS team rather than conventional oil and gas team. And as I said, next month I'm joining the CCS team as well, so I'm really excited. So I guess if you're really determined for it, then you could obviously look for jobs in this industry, or you could reach out to these organizations that are doing this work on it. And I know it's a long shot in future, but right now this is something that's really new. It's still developing, so there's still a lot of scope for new startups to come into play into this area. So yeah, it's I guess the field is open for you to play, and then it's up to you on how you want to play your part into it, I would say.
Thank you so much.
No worries. I think there are some questions in the chat that I would like to go through. So there is, what are the things we should consider while transferring CO2? Are there any risks? Isra, I already mentioned about flow assurance problems. Obviously, there's this problem of leakage, and there's a high cost of pipeline manufacturing, for example, if you want to store CO2 in offshore setting. So, for example, in Norway. So I guess one of the biggest challenges with transportation is the flow assurances, because if the CO2 temperature drops down, rises, or if the pressure drops down, then you could obviously have these hydrates formation or plugging in the pipeline that could be really dangerous. yeah, but apart from that, maybe someone from a chemical engineering background would know more about it, I guess. Um, what are the parameters we should consider during estimating storage capacity of the reservoir? So, Dalal, there are from a subsurface point of view, the first thing that we have to look at is the caprock integrity. So I told you there has to be a seal on the top, and this seal is basically a low permeability rock, or a rock in which it's really hard to inject something into it. In reservoir engineering, we have a term called capillary entry pressure, and this is the pressure that you need to enter into a rock. And when we talk about this seal or this caprock, this is basically a very, very tight rock, and it's really hard. The capillary entry pressure is really high. So when you inject high amounts of CO2 into the ground, you're basically increasing the CO2 pressure in the subsurface, and you can only inject until you reach the capillary entry pressure for the caprock. Because once you reach that pressure, then the CO2 will kind of leak into the caprock, and once your seal on the top is breached, then CO2 can just move up into the formations and then maybe to the fresh water or to the environment. So that is one thing that you have to kind of make sure, that what is the pressure rise due to CO2 injection, and that kind of defines or limits your storage capacity. And the other boundary condition is then pore volume. So it has to have some sort of pore volume where the CO2 can be. It has to have some sort of high permeability, so the CO2 can then move away, because we don't want the CO2 to be stuck at the injection point. So it has to move away from the well, so then we can inject more CO2. So, and then there are other things like heterogeneity, there is anisotropy, KVKH. So there are a lot of other things, but in general, the things that we look the most at is the storage. When we talk about storage capacity, is the pore volume and the caprock integrity. Then we have another question: is there any negative environmental impacts of such technology? Yes, there is. Obviously, when we talk about removing CO2 from the environment, we have to think about trees, because they live on CO2, they need it for photosynthesis. So we cannot just go out and remove all the carbon dioxide from the environment. We have to maintain some sort of CO2 concentration in the air. So right now, we are at 450 ppm CO2 in the air, and to be stable, below 2 degrees Celsius, we want to maintain it at 350 ppm, which is, I guess, doable with CCS. And then the other thing that we have to take care of is freshwater contamination, as I talked about, because CO2 can leak, and if it leaks out, then you would contaminate the freshwater supply for humanity and for living things and for plantation. And also, in general, doing CCS itself requires a lot of energy. So we have to make sure that when we do CCS, we are actually doing the net is actually negative emissions. I guess those were all the questions from the chat.
We have Mr. Faisal Mumtaz raising his hand. I guess he has a question.
Hey there, Yasser. Thank you very much for the wonderful presentation. I've thoroughly enjoyed your presentation. I've been keenly hearing you. Basically, I'm from P2M Berlin, and I understand a lot of your awareness in that region, because I also tend to have the same kind of awareness working for Berlin Wasser as well. So Germany's quite keen about this, and they tend to make sure that everyone's very well informed and aware about this. Unfortunately, here it's a bit comparatively lower. I'll jump to my question straight away. There was a reserve presentation slide that you showed, Dr. Binshams. Just have one small question there, if you don't mind.
Okay, let's see. Was it this one?
Absolutely.
Okay, wait. This one?
Yes, indeed.
Okay.
It's a small query which I don't understand yet. Maybe you could enlighten me a little bit more about it. To the best of that I have understood it, the carbon capture till this point, I've understood that the industrial contribution to the CCS is much more higher than the individual contribution. So my argument here is that to evaluate the CO2 emissions in regards with per capita, and not to look at it per nation, as mentioned by Dr. Shams, I still need to understand that a little bit more. If you can enlighten me there.
Yeah. So okay, one thing that we have to understand as a whole is these emissions, scope 1, scope 2, scope 3, they're not being created for no reason. Industries exist because there is a demand, and there is a demand because of people. If we right now decide not to use electricity in our house, then there will be no power stations. And if there are no power stations, there will be no oil and gas. So it all goes hand in hand. If Volkswagen manufactures million cars a year, it does it because people buy it, right? And this is why you cannot blame industries only or countries only. You have to look at the per capita emissions. Because in a lot of countries, so for example, I'll just give you an example because I've been in these two countries myself. If you go to Netherlands or to a developed European economy, they have so much awareness on this. You would see majority of the population using public transport, bicycles, and there's generally less use of cars. But last year I was in Dubai, for example, and the culture there is much different. The culture there is to use more cars, or even in US, for example. So we have to kind of understand how people live in a certain country or in a certain economy. I'm not saying it's always people's fault, but as I said, it goes hand in hand. I mean, industries exist because people have a demand.
Absolutely, Yasser. This is something that I'll be completely in line with you. Let me tell you just one thing for the other people to know as well. For example, in my headquarters office back in Berlin, at P2M Berlin, basically we don't even have ACs there. It's quite a posh AC office in a very nice location, and it's a government entity as well. But there are no ACs there, basically, barely any fans on the contrary. And temperatures, of course, go there up to 30 degrees Celsius. And here, if it's not 18 or 19, we immediately switch on the AC. So obviously, I completely agree there that there's a lifestyle difference there. One again, the question, if you don't mind me asking.
Yeah, sure, go ahead.
Just to understand the scope 1, 2, 3 a little bit more, do you know what's the contributing percentage of scope 1, scope 2, scope 3? Just to understand that the contribution, basically.
My short answer to that would be no. I don't know. I don't have the exact numbers on how much percent is scope 1, 2, and 3. But in general, it's really logical or natural to understand the highest emissions come from scope 3 because that's the consumer emissions. That's the end product emissions. So when Saudi Aramco produces oil, I'm sure I use it somehow. I don't know, somehow in the value chain, I end up using some of the oil that is being produced, and then it creates an emission, right? So the emissions are not created until the hydrocarbons are burned. So we have to understand it this way. When oil is produced, it goes to the refinery, it goes to a gas station, and then when we get it into a car, it is burned then. So at the end of the day, that's why I say per capita emissions are really important. But yeah, at the end of the day, most emissions, in my opinion, comes from scope 3, and which is why I also feel like blaming oil and gas companies in general is not fair, because yes, we do produce oil and gas, but we do it because there's a demand. It's as simple as that.
Just one small remark here. I understand completely the logic behind what you have just said in regard to scope 1, 2, and 3. And I just want to, this is my opinion. I feel the split of scope 1, 2, 3 is coming from a very, from a scientist background than more of an engineering background, because for me, I would rather emphasize and firstly look at the percentage of the most contributing scope, and probably consider the other one a little bit negligible and focus on solving the problems in that sector. That's how I'm thinking at the moment. Then on a minuscule level, at an individual level, basically. Thank you very much, Yasser. That's
yeah. Thank you for your questions and your discussions. I mean, I agree with you. There are different ways of approaching this, and this is something Professor Morton Blunt used to say when I was at Imperial. This was back in time when COVID had started, and no one knew what to do. So someone was imposing a lockdown. Someone was saying you have to wear a mask. Someone was saying you have to isolate. And a lot of industries were trying to create a vaccine. And this is what Professor Morton Blunt used to say. He used the same analogy. He said, when COVID started, we did not focus all our attention onto creating a vaccine. We went with a lot of different approaches to fight this problem. And in a way, climate change is the same thing. I mean, there is no one answer to the question or to the problem. There are a variety of different answers to the problem. Obviously, we need to shift our focus more towards renewable energy because that will reduce our Scope 1 emissions and Scope 2 emissions. We need to move towards electric vehicles. We need to kind of reduce fossil fuels. So all this is true. But at the end of the day, I've already shown you how all of this in general would still not allow us to achieve below 2 degrees C, and then CCS comes into play. So yeah, I agree with you. And I guess we need everything at the same time because the problem here is really big. And if we are to meet our net zero targets by 2050, then it's a steep mountain that we have to climb.
Yasser, one last opinion I want to ask you.
Yeah, sure.
Since we both come from a Berlin-based company, I just want to ask, Germany-based company, what's your opinion about Germany starting the coal factories back again and switching the existing one on?
That's something. I mean, me as a person, I'm someone who looks at the bigger picture always. So you have to understand 40% of European energy consumption comes from Russia right now.
Absolutely.
And I guess the remaining 60%, most of it comes from Norway. So last year, because I was living in Norway last year, working for Wintershall Dea in Norway, I know this first-hand experience. Last year, there was not enough rainfall in Norway, so they could not create enough hydroelectricity. This is what Norway relies on. Norway is one of the countries with least amount of fossil fuels in their grid. So they rely on hydroelectricity a lot, and they export all their gas, most of it to Europe, to Germany, and then to rest of the Europe. So last year, when the Norwegian gas supply vanished and when the Russian gas supply vanished, I mean, no one in Germany wants to pay 300 euros for electricity, right? Everyone wants cheap electricity. So then you have to find a way to fulfill the demand. And that's why I keep saying again and again, if there is a demand, we will burn fossil fuels. It's as simple as that. Because no one wants to freeze to death. This happened in Texas last year when there was a power outage and the temperatures fell below minus, I don't know how much. And yeah, I mean, the people died there. So we always have to think of the bigger picture. It's not a simple problem. It's a huge problem with a lot of different players, and it all goes hand in hand.
Okay, thanks a lot, Yasser.
No worries. But these are the kind of discussions I have at work every day. So for me, this is bread and butter now.
Well understood.
Yeah.
Thank you everyone for your questions. I would like to remind you all that we'll go for a group photo in a while. Meanwhile, I would like to call our SPE UOB Students Chapter President, Ali Yusuf Shakrullah, to present the appreciation certificate to Mr. Yasser. Ali, please come forward.
Sure. Thank you, Mr. Yasser and Amina. Can you see the screen?
Yeah.
This is for you as appreciation from us, and we'll be sending it to you, Mr. Yasser. Thank you for your information.
You're welcome. It was my honor actually to present this, and thank you so much. Again, I don't know if Nehal is in the call, but thanks to Nehal as well for suggesting my name. So yeah, for me it was a pleasure talking on this topic. And yeah, even in future, if you need any support, just feel free to reach out to me. And yeah, thanks again for inviting me.
Thank you, and thank you for the audience for staying around. If you would like, please, can you turn on your camera so we can take a group photo? Let me stop sharing. Thank you, everyone.
So I'll just send the reading list in the chat. If you guys are interested, then just feel free to have a read on these things. And I hope I could add some knowledge for you guys. And yeah, I hope this was a fruitful session for you.
Thank you so much, Mr. Yasir. Indeed, it was very beneficial and very interesting, very informative. Thank you so much for your time and sending, sharing your brilliant information with us. Thanks again. Thank you, everyone, for joining. Inshallah, we'll be getting back to you again with another webinar. Inshallah, we'll see you again soon. Thank you so much for joining, everyone.